Alright, welcome back to another problem, and this time around we're going to be working with a normal and tangential coordinate system. So let's begin. The pulley drags the cart over the curved track where the spinner rotates at a constant speed of 15 radians per second. If the shape of the track is estimated by the quadratic function, y is equal to x over 2 and the entire quantity squared, or the normal and tangential accelerations of the car at y is equal to 3 feet. Okay, so before we begin, I always like to just take a look at the assumptions that we're going to be using in our problem scheme. And so the first thing I'm going to assume is I'm going to assume that the cart is small relative to the track. Now, why am I going to do this? Well, I'm going to do this because I'm not given any dimensions of the cart. However, if I assume it's a particle, I can apply my particle dynamic equations, and that can make it a lot simpler to solve. Do I know if this is true? No. However, given the situation, I think it's an adequate assumption. So finish that up. To the path. Okay. Anything else can we assume? Well, there's probably some other things we can assume, but let's point out some other important facts. We know that we have a constrained system. Specifically, we know that the cart and the pulley are constrained, such that if we have that massless cord, and if we're assuming that it doesn't elongate or contract, we know that the two tangential velocities of both the pulley and the cart have to be equal. So we can write that the velocity of the cart is going to be equal to the velocity of the pulley, where the velocity of the pulley with a constant radius is just going to be r theta dot. Okay. So let's go ahead and calculate that. Velocity of the pulley is going to be equal to, we have 20 inches as the diameter. However, everything else is given in feet. So we can just convert that to feet now, and then we'll multiply it by 1/2 as well to get the radius. And we'll take that entire quantity and multiply it by 15 rad per second. And that's going to give us 12.5 feet per second. All right. So we have the velocity of the cart. I'll box that up just so we have it for later. Okay. Now what's next? Well, do we see here where it says the pulley drags the cart over the curved track where the spinner rotates at a constant speed? If we just said that the system is constrained such that they both have the same speed, if the velocity of the cart is going to be constant for all time, then since the tangential acceleration is going to be the time rate derivative of velocity, we know that the tangential acceleration of the cart is going to be 0. All right, that was quick. Now we've got one more bit to find, which is going to be the normal. Pardon that. Is going to be the normal component of the acceleration. Okay, we can write out our normal acceleration formula, which is going to be the tangential velocity of what we are considering squared all over the radius of curvature rho. We know the tangential velocity, but we do not know rho. So how can we get rho? Okay, well, we know that the track is estimated by that quadratic function. And there exists a formula that relates the radius of curvature to the function in a plane. And that's going to be rho is equal to 1 plus dy over dx quantity squared, that entire quantity raised to 3/2 power, all divided by the second derivative. Okay, I'll box that up because that is it's an important equation to have in your toolbox. I keep switching pages, my bad. Okay, so let's write out our function and take some derivatives. So we have, if we simplify the y is equal to x over 2 squared, we say y is equal to x squared over 4. We can write dy over dx is equal to x over 2. And then we can say the second derivative is just going to be 1/2. So if we take these three equations, we can write that rho is going to be equal to 2 times 1 plus x squared over 4 all to the 3/2 power. Okay? What is x? Well, the problem asked us for the tangential acceleration of the car at y is equal to 3 feet. So we can just plug in. So if we have y is equal to x squared over 4, plugging in for y is equal to 3, we can get that x is going to be equal to root 12. Okay? If we then plug that guy into our expression for the radius of curvature, we will see that rho is equal to 16 feet. I'll box that up as well. And yeah, now we're just about done. We have our value for rho. We have our value for the tangential velocity. And so I'll just finish that up. Box that off. So we have normal acceleration is equal to vt squared over rho. And then if we solve for that, we'll see it's going to be 9.765 feet per second squared. And that's it. Yeah, so just to summarize, we have our radius of curvature equation, which proved to be helpful in the normal and tangential coordinate system. We had constant velocity of our problem, which yielded a zero tangential acceleration. And then, just remembering that due to the pulley constraining both the cart, due to the rope constraining both the pulley and the cart, that made our problem a lot easier to solve. And yeah, I hope this video was helpful, and I hope you stick around for the next couple of videos. Thank you.